it's my great pleasure to welcome Professor Zheng to the special LCN seminar. So he is visiting from Northeastern University, where he's an associate professor in the mechanical and industrial engineering, electrical and computer engineering department. He's also the founder and president of Planck Energies, which sounds very interesting and intriguing. So he's also the director of the Nano Energy Lab. He's done his BSc in Tsinghua University in Beijing. After that, he went to Columbia University in New York. He's the recipient of many awards from DARPA, from NSF, from ONRL, and most recently the NSF Partnership for Innovation Award as well. He's got broader interests in nanomaterials and metamaterials for a wide range of applications, and I know that he's got about 10 of them, quite a lot of them in store for us today. So we're very excited to hear about your research. Thank you very much. There's quite a few of us here in person and also online, so thanks very much for bearing with us. Please put the questions in chats or raise hands, and we'll have discussions afterwards as well. So thank you very much. I will stop here and leave you to talk, please.
Yeah, thank you very much.
Thank you so much.
Yeah, thanks, Professor Hughes, for your introduction, and appreciate that. And also thanks, for arranging this, this visit here and give me a really nice tour this morning. And also thanks, Robert, and for setting up everything. Thanks to everyone, professors and students, for coming. And I'm Dr. Zheng. I'm currently associate professor at Northeastern University. I'm running the Nano Energy Lab. Currently, I'm supervising 5 PhD students and 4 masters. 2 of them PhD will graduate this year, and 3 masters will graduate this semester. So, and also I founded my own company, Startup Energies, actually last year, to commercialize some of the ideas or concepts you're going to see, in this talk today. And about myself, I'm a marathon runner, as it can be seen clearly. And why does that matter? Because this one clearly related to the research issue I'm working on right now. So after I crossed the finish line, someone just put this stuff over me, right? And when I checked that, what is that? Heat sheets. So what is heat sheet? What is the use of that? Clearly, the use of heat sheet, to keep it warm, right? And it's going to actually keep, the infrared and reflected, infrared, near infrared, visible, probably visible light, reflected back to your human body. As we all know, human body that emit energy out, and most of the energy emit out via thermal radiation. And the heat sheet, it's going to keep you warm. It's with really high reflectance. Actually, to my research, as what I'm working on is to design materials, and my job is to control the thermal radiative properties. Thermal radiative properties includes thermal reflectance, transmittance, and absorptance and emittance. That's it. And I have to work on a few materials during the past few years. And so we studied nanomaterial, micromaterials, and metamaterials is one type of the artificial materials. But today, in this talk today, you're going to see, I'm going to show you one special type or one interesting type of functional material. That is metamaterial. And also I put one word right in front of the metamaterial, that is cost-effective. So I will highlight the cost-effective functional materials in this talk. As you all study the nanomaterials, the nanotechnology center, and you fabricated nanomaterials using a different type of nanotechnologies, like the e-beam, lithography, or some other the nanotechnologies. They're really functional, and really useful. These days, we also study the nanomaterials, and my students, I believe, across oceans, still working on the e-beam lithography these days. We fabricate the metal surfaces for thermal emitters. But I had another idea. I just got this idea during the pandemic. So why not to achieve the same performance, mechanical, thermal, optical performance using the low-cost materials? So that's a cost-effective come from. So here actually I'm going to show you the functionalities of interest to me. Okay, like the wavelength selectivity, self-adaptivity, okay, can be achieved by the use of phase-changing materials. Thermal switching or optical switching also can be achieved by external magnetic tuning or the use of nanomaterials, nanoparticles, high temperature stability, and the self-cleanness and the fire retardant. So the applications. Today I'm going to show you, a few projects. Next slide I'm going to show you actually the table of content for one type of applications, energy. As I'm leading the non-energy lab, and my reason or the goal as an engineer here, okay, is to solve the energy issues, energy problems. So the materials today or the projects today you're going to see, I'm going to address energy and the energy-related water crisis. Both of them actually are global crises so far. So solar energy harvesting through thermal photovoltaics typically, and the passivity of cooling. I'm sure if the mouse is working here. Anyway, the passivity of cooling, solar-driven water desalination, and optical thermal sensing. And here, actually, I just showed you at the bottom right, okay, I showed you the materials of interest to me. Actually, you can see it's include everything here. Okay, the metallic, nano, polymer, dielectric materials. I mean, the nonsense to everyone here is this contains everything. But today I want to show you the material is interest to me these days. Okay, it's the one with multifunctionalities and with low cost. That's the goal. Okay. Well, here is the table of contents. As you can see here, okay, I prepared actually these slides a few days ago. So thanks for this opportunity. I just took this advantage, to summarizing all of my recent projects. Okay, so I didn't mean to bore everyone here. Okay, the people here, in person, the classroom, and the people also online, remotely on Teams. So I didn't want to show you only one project. I want to show you as many projects as I can. And all of those projects I have done in my group, during the past 2 years. So no more than 2 years. Okay, so there are still new projects. Okay, so I didn't show you some projects I've done more than 3 or 4 years. So today, as you can see, I'm going to show you the projects. The passivity of cooling. I'm going to use one slide. Summary in 2 projects, and then I'm going to highlight 2 projects today. One of the passivity of cooling projects. The other one, the solar-driven water desalination project. So I will use 6 slides to show you one of the 2 projects. About the cooling paper technology. And the second project here, the second topic here is the solar-driven water desalination. People have used different technology to desalinate ocean water. As water crisis, exists actually for a long time. Some countries, a few countries, where they do not have, they only have limited access to drinking water, to fresh water. So to desalinate the ocean water, desalinate the brackish water, high salinity water into drinking water is extremely important. I realize this one, and this topic is also one of the hot topics during the past few years. But I simply start from a different way. So I do not use any electricity, no pump, no RO technology. This is reverse osmosis technology. That's one of the popular approaches these days to desalinate ocean water. So what my idea is to simply take advantage of the solar energy, renewable energy, to desalinate ocean water. That's the concept. And then after these 2 projects, I'm going to show you one slide for the control of thermal emissions. And also I'm going to show you one slide, to control the thermal emissions, using the phase transition material, VO2, the vanadium dioxide, and the reconfigurable materials, that's made of the soft material, PDMS. And also one last slide to show you, summarizing 4 projects we have done actually in the last year, regarding the active control of thermal-related properties. The first one, passivity of cooling. So what is that actually? You may not be familiar with this topic. I'll just give you a general idea. We do need a convenient, comfortable environment actually in room or in buildings, especially during the summertime when exterior temperature is pretty high. So that's the use of the HVAC system, air conditioning. So air conditioning is really efficient, but it consumes electricity energy. My idea is, we can simply take advantage of solar energy to achieve solar cooling. People have studied solar heating for years, for decades, but solar cooling actually is something pretty cool. We simply use the solar energy to cool down the temperature, okay, inside, interior. Okay, in the buildings, the rooms, this is the concept. So radiative cooling is a non-conductive form of cooling. Passive cooling means, okay, it's a passive way, okay, it does not consume any electricity, simply rely on renewable energy, solar energy here. The principle, the mechanism of passive cooling here is, let's say we have a surface, okay, the surface, we have a material, the top surface is going to reflect of some of the light, okay, and it might absorb some of the wavelengths, and also some of the wavelengths might penetrate, okay, through this material. So that's why we have reflection, transmission, and emission, absorption. Let's imagine if a top surface of a material with extremely high reflectance, okay, let's say it can reflect 99.9% of the solar sunlight. So to make sure the sunlight cannot penetrate, okay, through actually this thin film, it could achieve cooling, okay, because most heating actually we feel right now actually totally because of the sunlight. But that is not actually the goal. That is not the mechanism of the passive cooling. The passive cooling is such a surface of the material can re-emit energy out to the outer space via thermal radiation, and it re-emit energy at particular wavelengths. The wavelengths of interest here are between 8 microns and 13 microns. It is a broadband window. It is a broadband Earth transmission window. As we know, actually, atmosphere of Earth's atmosphere is opaque. It's only opaque to some wavelengths, specific wavelengths. It's opaque to visible light, to infrared light, to UV light. Okay, that's the main issue. Actually, we are suffering from this global warming, a greenhouse effect. But the Earth's atmosphere is totally transparent to infrared wavelengths, particularly between 8 and 13 microns. So let's say if any material, okay, whose surface can emit energy between that, within that range, those energy, okay, those wavelengths can simply penetrate through the Earth's atmosphere, and those energy can get lost directly to the universe. So this is a concept that we have these days, okay, to achieve passive cooling, and also to eventually solve the global warming issue, probably. What is that? Why which we have the global warming issue? Because the human beings are really greedy. Okay, we design photovoltaic cells for what? To take advantage of sunlight. So we absorb sunlight, okay, and by PV effect, and then convert the photons, okay, those sunlight into electricity to drive, okay, the equipment on Earth. So if we simply stand out of the Earth, okay, and look at actually the Earth and the Sun and the entire universe, our Earth itself actually keep receiving energy from the universe, and we never give energy back to the universe. So that's one of the reasons, okay, why the entire Earth actually the temperature of the Earth rise up. To achieve a balance of temperature or energy for the entire Earth, we have to somehow give the energy back to the universe. So the passive cooling is one way. As if we do not tune the surface, we do not control the thermal emission property of the surface. Okay, so mostly, okay, the near infrared light, okay, will be re-emitted out, and most visible light will be reflected, okay, by the surface, and all of those wavelengths will undergo the multiple reflection and the scattering, okay, between the atmosphere and Earth's surface. So we still have, okay, this global warming issue. So that's the goal. And people have studied, okay, the passive cooling in the past 2-3 years already. People study actually the different materials, nanostructured materials, okay, like metamaterials, and some aerogel materials. I also studied that. We also have a few publications in other materials. But today, I want to show you one type of material, the low-cost material made of paper, recycled papers. Because actually, just 2 years ago, in 2020, so during the pandemic, actually, one day I went to my department suite, and I saw actually a bin full of recycled papers, used papers. I simply actually brought a bag of paper to my lab, and I asked my student whether or not we can do something with the paper. Why? Because paper, what's the color of paper normally? White. white color is good for what? It has really high reflectance, right? So automatically it has a high reflectance. And if we're able to tune the thermal emittance at the infrared wavelengths, okay, that can be great. So the paper itself, okay, can achieve the passive cooling goal. So this is the project I'm going to show you in the next few slides. And also we realize that, and also we realize the paper, the surface of the paper is hydrophilic. It may not be good for outdoor applications. For outdoor use, okay, as an engineer, actually, I thought actually we have to have self-cleaning property, which means the surface must be hydrophobic, or at least super hydrophobic. By contact angle, I'm going to show that later. We also confirm that as well. The other project we have done recently is based on the cooling paper. I call this one cooling paper because the material we use is made of cellulose fibers. Cellulose fibers are the main constituent of paper, print paper, office papers. After that, okay, we filed a patent and also founded my company last year. But right after that, I realized one big issue. I was questioned by so many industrial partners or people from 3M and National Lab. They said it's really cool idea, okay, the cooling paper is so good, but paper cannot survive under fire. Nobody's gonna replicate your house by paper, right? So the fire resistance is the key. I mean, and then we studied another type of metal paper, I named that, and totally we abandoned the use of organic paper, and we studied inorganic paper here. We use totally relying on the inorganic paper, we designed cooling paper, and this cooling paper could achieve the passivity of cooling. Okay, this idea, what is that? Actually, I just showed you. The surface has a really high reflectance to visible light, as well as high emittance to infrared wavelengths between 8 and 15 microns, as well as this material itself has really good fire resistance. As we burn actually this paper here and compare to wood and polystyrene. So after 10 seconds or so, this material not only it's not only fire resistant, but also fire self-extinguishment. It can extinguish fire itself within 10 seconds. This can be really good material. So this one, I mean, is not simply extension of my previous work because we totally studied different material, inorganic material. The first one I'm going to show you in the next few slides totally used recycled papers, cellulose fibers. In this one, we used inorganic material that is hydroxyapatite. Hydroxyapatite, that is the calcium phosphate. So the chemical formula is Ca5PO43. So this material is one of actually the commonly used material these days and the low-cost material. I'm going to show you actually, we also integrated the fire resistance actually into the cooling paper technology these days. But this I'm going to show you. Next 4 or 5 slides, I believe I'm going to show you the passive cooling technology we have. Like I showed you here, the passive cooling technology is the white paper or the surface of the paper can reflect most of the sunlight. And also it can emit infrared wavelengths through the atmosphere. And the material itself may not be white. It can be any color, actually we demonstrated that. The common sense is a white paper actually has really high reflectance, but it doesn't matter. We can still have the red dyed paper or green dyed, blue dyed paper, it doesn't matter. It might affect the solar reflectance a little bit, but the paper itself, the cellulose fibers themselves still own really high infrared thermal emittance. Let's skip some of the information as we have limited time, and also want to show you as many projects I can today, because the use of this project, I think I just want to show you what I've done and what I'm doing these days and what I will be doing, and try to give you actually the concept issue. So my expertise and what I can do maybe after the talk, if you're really welcome to talk to you, via email or in-person talk. So here I'm going to show you, we find out recycled papers, the cellulose fibers itself, with a really high reflectance, true visible and the infrared lights, up to 89%. It may not be good. During the past 3 years, a few group of people in America, in China, they have studied passive cooling a lot. One of the successful one is the cooling paint, the white paint, by a group at Purdue University. The white paint actually can reflect 99.9% of the sunlight. This one is only 89%. It's not good at all. Actually, I admit it. But considering the material itself, it's totally low-cost material and the raw material simply comes from the recycled paper, the daily life waste material. And this material itself, cellulose fibers, are friendly to the environment, unlike the chemicals. The paint are totally chemicals are toxic, okay, to the environment. And also, we studied this material, cellulose fibers, could also achieve a high emittance up to 92%, 0.92. It's still actually not perfect as 99%, but it's not bad at all. 89% of solar reflectance with 92% of infrared emittance. Actually, it is good for this material. And then, okay, we studied the superhydrophobic coating, the property. PTFE, this may not be a good material, I should admit it. Okay, but with the PTFE coating, we can clearly achieve the self-cleaning feature, okay, for the cooling paper. And then we must answer one question. So with the PTFE coating, whether or not this cooling paper still maintain a really nice expected optical thermal properties, okay, as what we want. So clearly, as we see here, the third bullet point. So with the PTFE coating, we demonstrated, okay, this one not only protects the contamination of the cooling paper from dust, okay, or from other, materials, but also it could reinforces, okay, the solar reflectance from 89% up to 96%. So it's really good, actually, we demonstrated it. So after we demonstrated, okay, this one experimentally, the next step, okay, to make it commercialized, okay, I mean, that's another story. But, I still want to show you, so we run some outdoor tests, okay, last year in 2021, outdoors, and throughout the 4 seasons. So 4-season test, we run the test almost every week, in summer and also in winter time, actually in Boston. On average, we're able to achieve the sub-ambient cooling performance of 6 degrees C. So what is that? 6 degrees C means we're able to achieve the cooling, okay, under, okay, less than the ambient temperature, the room, okay, ambient temperature by 6 degrees without consuming any electricity. So without the use of AC system, okay, we simply monitor, okay, the temperature inside of the house, okay, and outside the house with our cooling paper and without, okay, we're able to achieve 6 degrees C cooling, and the cooling power actually is still high, over 100 watt per meter square. And on the top right, I just show you the system will be set up. And I don't have time to go through that actually, but if you're interested, you can find the paper. So after that, and the simple question is, so if I want to commercialize this product, this is a really nice cost-effective material, okay, for cooling. So how am I going to do that? Okay, so such a cooling paper can be easily attached to, the building, the roofing of the material, the roofing of the buildings or the building walls. But color actually can be a problem. Once I talk to people, actually, people may not be in favor of white color, okay, the white buildings, okay, clearly, actually, no white buildings at all here, okay, in London. So if that's the case, so we have to dye the paper, okay. We study, okay, the dyed paper, and we find out, okay, so with different color dyeing, it does not affect much in the passive cooling performance. We also measured the reflectance and also measure the emittance for infrared light. You can see, okay, for the red dyed, for example, for red dyed and the green dyed papers, this can be comparable to the white cooling paper. So we demonstrated that. After that, I keep asking actually myself and my student. So far, we have already achieved, okay, the cooling paper, the concept, and how we're going to do that, okay, for the real outdoor applications. I'm going to attach the cooling paper to the buildings, but different types of building materials, concrete, wood, okay, or shingles materials. So this is what we're working on right now. And we already demonstrated experimentally the cooling paper, okay, performed really well, okay, and with integration to, okay, the concrete and the basswood. So without cooling paper, you can see, okay, the red curve for concrete and the blue curve here, okay, for the basswood. These are 2 materials that we commonly use for building materials. And with the cooling paper, clearly, the reflectance is pretty high over the visible light range and the near infrared light range, and also with a really high emittance. That means with really low reflectance, okay, in the first window of atmospheric transmitted window between 8 and 13 micrometers. That's the concept. So we demonstrated, okay, the self-cleaning feature, and it's gonna extend the life cycle of the material. After that, I also ask, ask my student, so whether or not we could keep reducing the cost, because the topic of this presentation is cost-effective materials. The use of recycled paper clearly low cost, reduce the cost, but how we can keep reducing the cost? can this material itself recycle? This is the question should be answered. We need to answer that. So we simply actually this fabricate the paper and use the high-speed blender actually. Use the high-speed blender to recycle the paper ourselves in the lab. Here I want to show you actually we have this video clip here to show you how this recycled paper. Anyway, this is fine. It is fine. This video just shows you like we use the blue dyed water to show you how self-cleaning the surface. Okay, it is. Okay, doesn't matter. You can imagine that actually. And also we use high-speed blender, okay, to make a paper pulp in our lab. So we really made actually the paper using the recycled paper, and then we measured okay the reflectance of visible light and emissivity okay for infrared light of interest here. As you can see here, almost the same. So recyclability does not actually compromise okay the expected cooling performance. So this is something I want to show you. After that, we also run okay some mechanical tests, as I'm from mechanical engineering department, okay, not from the material department. So we need to run some mechanical tests okay to demonstrate this material is mechanically robust. Okay, so stress strain curve, as you can see here, this material itself okay can be comparable to artificial wood. Not bad at all. Only for 3 layers. Only for 3 layers of cooling paper, it could be comparable to wood. And also we run the surface absorption test okay in our lab. Okay, for example, actually we use the 400 grade silicon carbide sandpaper, and we just stretch okay the cooling paper in one direction around 10 centimeters, and then rotate it 90 degrees, and another 10 centimeters. This is one cycle, and then we repeat it for 100 cycles. And then after that, actually, we just confirm okay the stability of this material. Okay, so this is the end of the Passivity of Cooling project. The second concept, desalination. So I explained to you actually, at the beginning, so the necessary, okay, how important actually to desalinate ocean water and transform ocean water into drinking water these days. And people already use okay the RO technology a lot these days. Okay, so if you go to okay the countries, okay, some factories, they simply use the reverse osmosis technology. But this time actually, I just would like to use the solar energy. So just like okay the passive cooling, the concept, I would like to take advantage of solar energy. So I always have a goal in my mind. Okay, my idea is not simply replace the existing system with solar energy. No. For example, the first project regarding the passive cooling. So using the cooling paper, this concept, I didn't aim to totally replace 100% replace the use of HVAC system. But even though we can replace only maybe 5%, 8% of the use electricity, that can be great. It's the same thing here. I didn't dream okay to simply rely on solar energy to desalinate ocean water to meet actually this requirement for the people on Earth. But if we're able to take advantage of this technology to solve some of the problem, that can be good. So I'm going to use the 2 slides with the 4 different projects to show you what I've done during the past 2 years. The first one here, we designed a 2.5 dimensional, 2.5D evaporator. It's just actually a concept, just a term actually we invented, 2.5D. People already studied 2D structure and the 3D structure, okay, for different applications, in different research fields. For water desalination, people also have okay, the 2D and the 3D structures. So what is a 2D structure for desalination? Like for interfacial heating system. Interfacial heating system is a thin film structure, multi-layer structure that is float at the water interface. Okay, this is absorbs sunlight, and also this material itself is extremely water absorbent. It can absorb water actually through the micropores, microchannel inside, and to reach the top. And the water can be evaporated out okay, by the solar energy. And this is the 2D structure. And the 3D structure is okay, people designed okay, some smart tree, okay, like a tree. Okay, so they have a root, okay, just immerse into the water. They have a trunk, okay, serving as okay transportation path, and also they have a leaf, okay, and this serves okay as evaporation device. So it's really, really fancy, but complicated, okay, in manufacturing, and also for outdoor application. 2.5D, this concept is we still use the 2D structure, that's a multi-layer structure or thin film structure. We just leave it up. Really simple enough. As engineers, why we cannot do that? Okay, just like these days when people set up okay the PV panels on roof, it's not a flat at all, right? It always has an angle that fits into the sun. So why we cannot do that actually for desalination project? Simple concept I had actually 2 years ago. So leave it up. Just made an angle of that. And clearly, one of the advantages is with the 2 surfaces, the sunny side and the shady side. Even though Chinese said that does not contribute much, it still work, contribute a little. And also, to study this material, we targeted copper, the porous copper foam. Okay, the porous foam itself is hydrophobic. But to achieve the water desalination project, we have to make sure water can be climbed up, okay, to cover the entire surface of the material. So this material itself must be hydrophilic. So to do that, what is the concept? We find out a way to oxidize the copper foam. So now actually we obtained oxidized copper foam, totally changed the color to dark, to black. Because in my research lab, we like black color. Why? Because black means black body of, okay, it's going to absorb most of the sunlight. And also this material itself is porous material. It has micropores automatically. We study the different pore size effect and also the porosity effect in this project. I want to show you. So we are able to achieve the really nice water absorption water evaporation performance through this project. Top right corner, you can find out the SM images. Okay, on the left in figure A, it's only the copper foams itself, copper foams. Figure B, this is the oxidized copper foam, the CuO or Cu2O. Okay, so you can see there's the blade-like structures. Because of the blade-like nanostructures, this material becomes extremely water absorbent. So we achieved a nice evaporation, and then we continue. Last year, I also asked my students, so after that cooling paper project, I said, whether or not we can simply find some waste material, like paper waste material. Okay. So I got this idea, about 2 years ago, still during the pandemic. So one day, actually, I drove to the local dairy, local farm to get a dairy. So while waiting, so I saw actually the cows, horses, the just actually on the farm. So the full of actually the cow dung, or manure, cow manure. So I simply asked the owner of the farm actually whether or not actually you can contribute something for free, a bucket of cow manure. I want to do research. Interesting idea. I talked to him and then he loved. He gave me actually for free. Clearly, I brought this bucket to my lab and to my student and showed my student actually. So what we did, we simply carbonized it. We carbonize this material at high temperature, at 400, 600, 800 degrees C. So you can imagine, and in vacuum, in vacuum condition. So you can imagine, so after high temperature combination, carbonization process, what remains? Natural carbon, just a carbon. Because the manure itself, just fibers. So after high temperature carbonization, just the natural carbon remains. It does not consume any nanotechnology, nanoparticle, or nanofiber at all. We obtain the carbon from agricultural waste material. This is the concept we have. So as if the dried manure and after 600 carbonization, we obtain totally black. Like I said, actually, I like this color. It means it has a really nice solar absorbance. And it's can achieve over 95% of solar absorbance. For this material, we did not add any chemicals at all. No chemicals. The only thing we need to do, just carbonize it, in a vacuum furnace. That's it. That's it. And also, we are able to achieve pretty high water evaporation rate. I'm going to show that later, for comparison. And the people might ask me, so whether or not if I worry about some bio stuff, bacteria. Clearly no. So after 600 degrees C, so no bacteria can survive at this really high temperature. And also this material itself can survive pretty well in water. It will last a long time. Because we didn't imagine this case like that. We thought actually we might need to add some bonding material, adhesive material, gluing material to bond those carbonized materials, but no. Still, actually, we didn't know actually what's the reason of that, but actually we found out this if you simply let this material flow at the water interface, it just lasts as long as it can. You won't see any part actually falling apart from that. But we did find actually an issue, for other projects. We're going to see that next slide. So after this farm waste, agricultural waste material, another material we studied actually last year, ocean waste material, biomass. As actually I'm from Boston, actually pretty close to the ocean. Now we simply collected some ocean water from the Boston Harbor and for our test. And also, I asked my student, as this application is for ocean water desalination, whether or not we can make a nice cycle from ocean material, okay, to benefit ocean. It's ocean to ocean cycle, and then we change our mind to ocean biomass materials. What they are, okay, like I said, we pretty like the dark black materials. So what are the black materials, okay, in ocean, like cuttlefish ink? Spray ink. I fish, so I know I should cuttlefish ink, okay, totally black. So we simply purchase some cuttlefish ink in liquid form, and we dry them. And also in our lab, we have a ball miller, so we're able to make, the carbon nanoparticles, okay, from the cuttlefish ink. And the average diameter of the carbon nanoparticles refabricated through the cuttlefish ink is only 10 nanometers. It's pretty well, and but the raw material is cuttlefish ink. And also, at that time, actually, our goal is to study hydrogel material. To study hydrogel material, okay, and we need a bond, skeleton of the material. So which material can serve as a skeleton material for hydrogel, and also the material is for ocean? Chitosan. Chitosan comes to our mind. Chitosan is just a powdered form of, like a lobster shell or crab shells. Okay, so you can see two raw materials we use here, cuttlefish ink and chitosan are totally biomass, ocean biomass. And also we made our chitosan hydrogel, and also we achieved the high rate. I'm going to compare them later. And the one last project I'm going to show you for desalination is we studied paper waste material, agricultural waste material, and ocean waste materials. And also, this time actually, I changed my mind actually to forest waste materials. And also, during the pandemic, 2 years ago, actually, I went hiking in Boston, local area, and in the fall, in the October, September also, I just found out actually, this national park is full of the tree leaves, oak tree leaves, maple tree leaves. The other day, I just brought actually the 3 large, trash bags to collect tree leaves, because I realized we might be able to do something with the tree leaves other than burning them. So we collected the 3 different types: maple tree, red maple, yellow maple tree leaves, and also the oak tree leaves. I brought them to my lab, and also we separated the stem and the leaves, and I will still use the carbonization, blend them, and use the carbonization process exactly as what we did to manure, to cow manure. And of course, we can obtain black stuff, but this material was not as good as manure. Why? If we soak this material into the water, it's going to fall apart. So within 10 or 15 minutes, surprisingly bad. So if we repeat exactly what we did, okay, to manure, we compare them. We have a dried manure, or we have a carbonized manure, and also have a carbonized tree leaf samples without adding any chemicals. Manure actually can last as long as it can, up to at least 1 month. 30 days, actually, we can see that this material is still one part, but actually tree leaf problems. But to solve this issue, so we had to add some adhesive material into this carbonized leaves. But my idea is still use the natural material. So this adhesive materials should also come from nature. So we chose guar gum. So one type of the natural gluing material. So we mix them up together. Okay, this total material is still natural, made of natural materials, and turns really well. So here I want to compare the water evaporation rate for you, okay, throughout this project, this 4 projects. People have studied, okay, the water desalination, the solar-driven water desalination project, during the past 2-3 years. And let's say, if we have a cup of water, okay, or tank of water, without any material, without any interfacial heating material on top, only totally through the natural evaporation process. Okay, the evaporation rate is 0.41, 0.42. What is a unit? That is liters per meter square per hour. So per unit time per 1 hour per meter square per unit area, it could evaporate up to 0.41 liters of water. Okay, so keep this number in mind. And during the past 2 years, a lot of groups from MIT, Stanford, actually, they use hydrogel material, okay, to achieve really high rate, up to 1.4, 2.4, 2.6 also. In our group, carbonized manure is extremely low cost material, achieved up to 5.3. So 5.3 liters per meter square per hour, and bio-ocean mass 4.6, and tree leaves project 2.0 or something. So you can imagine, okay, the carbonized manure actually could achieve the highest rate so far as we know. And this project actually I already contact with 2 Indian companies these days, try to commercialize this product. As one of the company in India actually who reached out to me, they have a farm, they own a farm, over 1,000 cows. So they can supply, this cow manure easily. So this can be really interesting and useful project I have. Next few slides, I might skip some of them. I just want to show you here. So these days, there are 3 different types of heating. Bottom heating, not efficient at all. Bulk heating, heat up the entire bulk of water. The evaporated water also is not actually good in comparison to interfacial heating. Interfacial heating, just the one we work on. The carbonized manure, 2.5D, they all belong to this category. Interfacial heating. So we have a material, this material can just flow at an interface or with angle. So interfacial heating. And next few slides I'll show you, this ocean-to-ocean cycle process, but I already explained them already, so I don't have to go through them. I can go through them really fast. As an images, of the cytosol, and as an images of the cuttlefish ink particles, the nanoparticles we have, and we combine them and made the cuttlefish ink and the cytosol hydrogel. So you're able to see the microchannels. This material itself is extremely absorbent to water. And also we run the mechanical test as well and run the desalination test. We have the solar simulator in our lab, and also we have a digital scale to monitor the change in mass, and we record the temperature up to 90 minutes also. And then we only take the stable the data from 30 to 90 minutes, and the temperature we measure. One thing I want to show you, so this material itself, original idea was, so we have a direct contact. So we have our carbonized manure or the cuttlefish ink, the cytosol hydrogel directly flows at the water interface. It was a concept. It does evaporate high water at a higher rate, but it may not be ideal. Why? As with direct contact, you can imagine, the top surface serving as a solar absorber is absorbs sunlight, and the heat can be conducted to the bottom surface. So it's totally a waste of energy. All of this energy will be disseminated to the water. So this is something we should try to avoid. And then we updated our system. So we place this our material on top of the cotton wipe and with the cotton wipe to absorb water. So this is the concept only for the ocean biomass project, not for the carbonized manure project. And also we demonstrated one important thing. So as we have done this project, we kept receiving comments from reviewers. One of the reviewers asked a reasonable question: salt rejection. Clearly, this is really important. We have to solve this issue. The goal of this project is to take advantage of solar energy to desalinate ocean water, and after that, we can collect the evaporated water, drinking fresh water. But where are the salts? Where are those salts? Salts might block the micropores, microchannel, in the system. So we need to aware about that. So we demonstrate, all of those materials that we studied so far with the salt rejection performance. What is that? So as you can imagine that, so under 10 signs, and we concentrated on under 10 signs, clearly we can see all of those salt, sits on top of the surface. It's gonna block the pores. But the problem is we're not able to use this system 24 hours a day. We let this material floating at the water interface under the sun, solar exposure, only for the daytime, no more than 8 hours a day, 6 to 8 hours a day. The rest of the day, the material itself is still water absorbent. The water keep actually absorbing through the micropores, microchannels, and they're gonna wash away all of these pores, down to actually the bottom, down to the water bulk. That was the concept, and we demonstrated that. So you see, after 2 hours without the solar absorbance, in the dark room, all of the sun actually has been go back, just downwards to the bulk water. So we demonstrated this one already. And this system actually has been already set up in Egypt right now. So during things last year, actually, we already make this system set up in Egypt. So hopefully actually one day I can go there to see this system. So next 3 slides, I want to show you the different concepts or different projects we have done in past 2 years. So the first project regarding the passivity of cooling. Second project regarding the solar-driven water desalination. Third project, as I mentioned at the very beginning, my research interest is to tune the thermal radius properties, to tune the thermal emission. Right? So how do we do that? There are different ways, different mechanisms. First idea is, all I had, is to use multi-species nanoparticles. It seems really simple, but people have not done that yet. Before I did it, people studied nanoparticles or microparticles a lot. Okay, and nanoparticles, single species can be used in different applications. Okay, for different applications. For example, people can use the gold nanoparticle to track the lung cancer, probably. But mostly, people only use one single species nanoparticle. Okay, they mix up nanoparticles into the softer material or thinner material and study the mechanical, optical, electrical properties. My idea is whether or not we can study multiple species. Why? Because we all know one material, one type of one species nanoparticles, each could emit specific wavelengths. Okay, I mean a narrow band emission. Okay, at a specific wavelength. And if you have two different types of nanoparticles, okay, and each of them could emit one or two the different narrow band emissions, right? Something like that. And why did I have this idea to use the multiple species is my goal was to open up a broadband window. For example, for passivity of cooling, we would like to obtain a broadband window between 8 and 13 micrometers. That is the goal. That is the goal. But how to do that? If we can find out more than one materials, and each of them actually could emit the narrow band, and if they're overlapping, and they do share the common wavelength range between 8 and 13 microns, we might be able to achieve a broader band window. That was my idea, and we demonstrated experimentally. So we found out actually the two nanoparticles here, silicon nitride and the boron nitride. And the host material, the matrix is KBr, the potassium bromide here. So this is the first time actually we studied the more than one species nanoparticles. And you can see, if we simply use one species silicon nitride, you're going to see two narrowband emissions peak. Okay, at 8.5 microns and at 12.2 microns. If we simply use the boron nitride, you're going to see other two peaks, 709 and 12.445 microns. So you can imagine if we combine these two materials, we might be able to see 4 separate individual emission peaks, or we might be able to open up a broadband. And we did this run totally experimentally, and we found out that we're able to open up a broadband thermal emission window. This is the concept. I didn't do actually fundamental work, but I simply didn't do the theoretical work, but we didn't conduct the measurement ourselves. So this is the one. So we already achieved that. So that gives us some ideas. So in the future, if people would like to open up a broadband window at a particular wavelengths for specific applications, you might need to look out for the information. Look up the materials which could actually emit narrowband emissions during that range. And you can combine them. That might work. After that, what other concept? People also ask me, your passive cooling idea is really really good, but how do you control that in different seasons? Let's say we need the cooling in summer, clearly actually we do not need it in winter time. So the smart control here, the self-adaptive control, it is important. And we still use the same concept here. As you see here, we still use KBr as our matrix material, but more than 2 species. Really complicated. This is just a concept. I'm working on this one right now, actually theoretically, not fundamentally. You can see, so other than the use of silicon nitride and boron nitride, we also added VO2, the vanadium dioxide. VO2 is one type of phase transition materials. It's from solid phase to solid phase. It's from metallic to insulating phase. So this is something that we could do, clearly. So with the inclusion of VO2 nanoparticles or VO2 thin films itself, it could turn this material on and off. It could turn on. Means we can open up this window. For the use of cooling, and we can also shut it on. Turn it off. To make sure it's not a cooling at all. It's gonna keep it warm. Just turn it off. But why? We also try to add 2 other species, silicon, tungsten W, and ICR, the strontium, and the particles, because so with the inclusion of tungsten and strontium and the particles into silicon into vanadium dioxide, we are able to lower the phase change temperature, okay, down to room temperature. Because the original phase change temperature of VO2 is 68 degrees C, 341 Kelvin. Okay, this may not be good actually for outdoor application, for building applications. So we must find a material with a lower phase transition temperature. To lower that temperature, okay, we consider to add these two nanoparticles. And people already demonstrated that, okay, so with the tungsten and SR, either or, this could lower the phase change temperature of VO2 from 68 down to room temperature, 25 degrees C, or even lower. But actually, we are not doing an experiment right now, so we haven't demonstrated this one. We have to do that ourselves to confirm that. And another slide I want to show you, another project we have done. We also use the phase transition material, VO2, to study something else. This time, okay, we studied the thermal rectification device. What is that? That's like we control the heat flux, okay, in one direction, not the other way. I got this idea, I bought this idea from electrical engineering, like diode, electronic device, electric diode. We can simply control, okay, the electric diode can control the current in one direction, not coming back. Whether or not we can control the thermal signal, okay, in one direction, not coming back. Okay, so that we should be able to design a thermal diode. That's the one I want to show you. So we made it. So we have two structures, and by taking the near field thermal radiation, so we could obtain a really high thermal radiation, okay, at the nanoscale gap, the 100 nanometer gap. And the bottom surface here, as you can see, the red color here, the surface gradient structure is VO2, vanadium dioxide, okay, fission material. I use it, and yellow one just the gold. On top, okay, the top part, the light blue is BN, boron nitride. So nothing new, okay, this still material should be used. And we calculated, okay, the heat transfer, okay, and across the phase transition temperature, 341 Kelvin, by 1 Kelvin up or 1 Kelvin down. Okay, so plus or minus 1 Kelvin, plus minus 2 Kelvin, plus minus 5 Kelvin. And also we defined the radiative heat flux from bottom to up, forward. I said there's a forward direction. And from up to down, or downwards, okay, just downward, backwards. So we just need to calculate the ratio of these two heat fluxes, okay, the forwards and the backwards. Without the use of phase change material, you can imagine this ratio should be 1. So the forward should equals backward. But with the use of phase change material, this ratio is greater than 1. Okay, so far we're able to achieve as high as 17. As high as 17, but actually in the paper we published last year in 2021, in APL last year, we already increased, okay, this ratio from 17 up to 146. So that is the highest actually the ratio we obtained so far. Across a 10 Kelvin temperature difference means we simply change the temperature by 5 degrees. So 331 plus or minus 5 Kelvin. Okay, so simply measure that. Or simply calculate the heat flux across the 5 Kelvin. And after we studied this concept of thermal diode, I asked myself, what further I can do, okay, with this project? What other devices, thermal devices? So now, like I said, we have a thermal diode, okay, with 2 parts, 2 terminals. Imagine we have 2 thermal diodes. We place them back to back. But now you have 3 parts, 3 terminals. What is that? Transistor. So we might be able to design a thermal transistor. This is totally non-contact mode because we use the thermal radiation, so non-contact mode thermal. So we have a source, we have a drain terminal, we have a gate terminal. We just need to change the temperature of the gate terminal, and we might be able to amplify the thermal signal here. That's our concept, and we also studied that. And currently, we already demonstrated it does have the amplification factor effect. So we achieved up to 2.24 also. It is not high, I know, but this concept might give some insight in the future. So we might be able actually to design some thermal electronic devices, logic devices in the future, like diode, like transistors. So all of this project we published 2 years ago. And also one project today, here. This one was published in 2018. okay, more than 2 years ago, like I said. But the reason I showed you here, because next slide, the last slide, I'm gonna show you 4 projects, totally based on this mechanism. Okay, that's why I'm gonna show you that. So my goal is to study, okay, the dynamic tuning of thermal emission. So we can use different mechanisms like inclusion of multiple space nanoparticles, or we can use on the magnetic materials. We also published a paper last year, the external magnetic field to tune the optical property. And also we can use a phase change material. What else? Mechanical deformation. Really simple concept. So if we're able to design and fabricate our pattern, our metal surface pattern on top of a soft, reconfigurable, stretchable material substrate, this material actually can be reconfigured. So the material we chose here, bottom is the PDMS, clearly softer material, and we deposit our boron nitride on top. It's still common. Okay, just give this concept here. So under mechanical deformation, so you clearly the grating of the surface, the period of the grating elongated, and we demonstrated this one. So with only, this can be pretty fast. Okay, so 10% deformation could yield up to 25% change in the heat transfer. So let's say here the 10% strain, it could reduce the heat flux from 36 down to 27 also. So more than 25% reduction. So you might ask, 10% deformation is too large, but clearly no. It's for nanoscale. Okay, so if we're able to make a pattern, such as grating structure, with a period only 10 nanometers, so 10% deformation is only 1 nanometer. So 1 nanometer deformation could yield 25% change in far-field thermal radiation. So this concept can be used to design a highly sensitive optical thermal sensor. Based on this concept, this is the last slide I want to show you today. And this is the last slide. So 4 projects were published last year. You can see they all based on this concept here. So we further study the far-field thermal radiation and the near-field thermal radiation. Okay, so we make our one-dimensional surface grating structure on PDMS, and also we make our two-dimensional surface grating structure on boron nitride. And we study, okay, so under mechanical deformation, so how it's going to change the thermal emissions. Okay, so you can imagine the first one on the top left. So we also studied these 2 different scenarios here. So scenario number 1, okay, so under stretching, so it's going to extend like that. That is too ideal. It is not practical at all. And the scenario number 2, okay, something like that. And the bottom left, you can see we also studied the 2-dimensional grating structures here, other than 1-dimensional. We'll also have 2 different cases like that. And the top right corner, okay, the one we published last year. And we used the mechanical deformation, this mechanism, to achieve the self-adaptive control, okay, of the passivity of cooling, to turn on and off, other than the use of multiple species nanoparticles. And the bottom right one, okay, 4 nanoscale thermal radiation. Okay, so last 2 slides to show you actually the equipment we have. So if you're interested in that, actually in the future, I'm trying to establish some collaboration with you. So actually, I like to make my equipment actually in my lab offer to you. So we have 2 spectrometers in lab. So other than 2 spectrometers, okay, we have almost all accessories for that. So all of these accessories, okay, are more expensive, okay, than the spectrometers we have. So one cover UV visible to 2.7 NIR. The other one we have a longer waveform of FGR, and also we have accessories. We have 2 integrated spheres, okay, polarizer and different kits, okay, for the different measurement, for different temperature, for vacuum, and also for diffuse reflection measurement. And also the everything we have in my lab. So we have vacuum furnace, and up to 1300 degrees Celsius. We also have another furnace, the Marfil furnace, that could heat up the sample up to 1700 degrees Celsius in my lab. And thermal camera, solar simulator, freeze dryer is used to fabricate hydrogel material. That one is used to measure, okay, the contact angle. Oh, I forgot to mention that. So for the cooling paper one, okay, I mentioned that to you. So original cooling paper, the cellulose fibers, okay, it's hydrophilic. The contact angle actually is around 85 also. And with the PTFE coating, okay, we are able to change the surface from hydrophilic up to super hydrophobic, not only hydrophobic, because the contact angle, okay, turns out to 165 degrees. So and also we run the outdoor test. We just set up our cooling paper at the roof of our engineering building for 1 month, 30 days, and bring it back. It still maintains pretty nice mechanical properties, including the contact angle up to 165 degrees. And yeah, pretty much. It's the photo about my group, my students, and knowledge all the funding agency received. Thank you very much.
Thank you so much for an amazing well-run tour of all these fascinating
my pleasure,
materials and applications. We've got time for questions, negative time for questions, but if anyone in the audience has some points. Yeah, Dan?
I was really curious, for this carbonized manure, what was it morphologically that was making it so much more superior to the other materials you were testing?
The concept itself is really simple, as you can see here. So the only thing we need to do is we collect the manure from the farm and bring it to lab. And then step number 2 is carbonize it. We do not need to filter it, we do not need to wash it out, okay, just carbonize it. And then that's it. It itself already made its product. And the step number 3, actually, I forgot to mention, is we simply use hydraulic heat press to make a brick. It's just like a brick. So it's a brick-like sample we're able to make, I think it's can. Okay, and just use it. So the idea is we do not want to add any chemicals or any non-natural materials into this carbonized manure. And also it's a turnout really nice evaporation rate. Yes.
What was the mesh structure that you were getting? Why was it so much more stable mechanically compared to the other ones? Was it just the interconnection of the carbon from when you were doing the processing? I mean, why were the leaves falling apart but the manure wasn't? I mean, is this just because of how it is structurally, biologically before you did the process?
Yeah, really good question. We tried to answer it. We found out actually because of the bond, the carbon-carbon bond. Yeah. But to be honest, actually, it does not convince me, I know. But actually, we demonstrated that because of the strong carbon-carbon bond, actually, I mean, it does really good job. Mm-hmm. But even though actually without that bond, and like I say this one, for the tree leaf project, okay, we see this issue, right? But we also demonstrate this material itself, carbonized tree leaf, also comes with really high, strong carbon-carbon bond. So still, it's an open question, so we don't have a clear answer. So why this carbonized manure could last long actually in water? But it does work. Yeah. It does work. So that's it. Sorry, actually, I do not have actually a good answer for that. But to me, so I did a lot of theoretical study before and also fundamental study on nanomaterials. And these days, I totally changed to applied research. So if we're able to make it, to demonstrate it works.
Yeah. We have a question from the chat here on what is the frequency or the speed of the heat flux modulation that you could achieve with the phase-changing materials approach?
That is a very good question.
From Peter Petrov, who's at White City or
yes.
Home. Yes.
So this frequency is not high. It's not high. And I want to give you a number. So for VO2, vanadium oxide, its phase change, okay, it undergoes phase change process within a really short time frame, down to 10 picoseconds. It's going to change pretty fast. But in our lab, we cannot do that, and that's why we simply give a gradual change temperature. Okay, so we give a 5 Kelvin temperature change. So initially, we lower temperature by 5 degrees, and then we increase up to 10 Kelvin. Okay, and we do not control the speed at all. We simply measure the radiative heat flux, okay, at static. So that's why I do not have.
What's the potential? Do you think that in terms of heat transfer, is this something that could go to a high speed exchange?
Like I mentioned that actually, phase change could actually occur, within 10 picoseconds. Okay. So if we're able to heat up or lower the temperature, that fast actually.
So it's only limited by,
that is true, yeah. But
the external
experimentally, we're not able to achieve that actually in our lab. So if we're not able to achieve, down to picosecond or millisecond in our lab, so for us, we just conduct it as static conditions. Okay. Yes. Thanks, Peter, for this question.
Thanks. Okay, yeah, please.
The reflective paper, you said at some point you switched to inorganic
yes.
paper.
Yep.
what does that actually mean?
Okay.
I've not heard of that term. Is
Yes.
that still from a recycled paper feedstock,
No,
or is that
no.
something completely
The
different?
inorganic paper actually is totally different from organic paper. We do not use any cellulose fibers. I simply use the calcium phosphate. The material name is pretty long. It's a hydroxyapatite.
Yeah.
We use that.
Sure.
So we simply use this material itself. And in my slide, I'm not sure if you were aware. Actually, I do have an SM images of the inorganic material. We still see the fiber-like structures, exactly like the cellulose fiber. So that's why I still call this one paper, but it's not a paper at all.
Yeah.
We do not use the recycled paper or inorganic material.
What is the feedstock of that hydroxyapatite then?
I didn't have an answer actually for that.
Okay, but is it still something natural? Because
It is something
a lot
natural,
of your
yes.
research focuses on,
Yes.
going out into nature and
Yeah.
finding the materials, or is that synthetic?
Yeah, we didn't simply find this material. I mean, suddenly it came to our mind. Actually, we read this, paper and found this material,
Sure.
and as we know, this material is still abundant. Okay, and yes,
Is it in bone? Appetite?
that is true. Yeah, that's a bone, it's human bones. Yeah.
Well,
Oh, yeah.
we'll see about the ethical.
That is true. Yes.
Yeah. All right. Two quick questions. One from Harry.
On these sort of passive cooling technologies, if the sort of planned use would be to put them on sort of building roofs and things like this, how quickly do they degrade?
Integrating it.
Degrade.
Oh, they degrade. Okay. Yeah. Very good question. As right now I'm commercializing this product, so actually I have to answer all of these questions. One thing is, this cooling paper may not only be used for buildings. It can be used almost everywhere, like refrigerant trucks. Okay, the refrigerant trucks and also vehicles, cooling tent, almost everywhere. It can be large scale or it can be small scale. And lifetime. Lifetime is a key issue here, and people question that. We cannot, answer this one correctly because currently in our lab we demonstrated the lifetime up to 1 month. For published paper, actually, up to 1 month, and after 30 days we brought this back to our lab and we were not able to run this up to longer time, 6 months or 1 year. But like I mentioned, why I mentioned actually the use of the recyclability. Even though this material actually does not function well after 1 month, so what? Scratch it down and recollect them. That's it. That's the concept. So we don't have to worry about that, especially for small scale application. You cannot imagine to change your roof almost every month, but actually for small scale, that might work. Yes.
Okay. Right. One last. Okay. Yeah.
I was curious for your foam, which you're making this 2.5D structure with. How exactly were you planning on orientating it this way if you wanted to use it for application? How do you keep it at this non-planar angle?
A 2.5D project, are you talking about that? Yeah. Like I mentioned at the beginning, for that project, I got this idea from the PVCL, right? So PVCL usually, have a specific angle for the location of cities. Okay, you have a different angle, tilt angle. For this one, no, you do not need to worry about that. The only idea I got this one from that because we might able to tilt up, okay, with the angle, tilt angle. This surface may not have to face it directly to the sun. It doesn't matter at all. The only angle actually we tilt up, okay, is to make sure the water can climb up to the top, to reach to the top. We study actually the angle from 30 degree up to 60 degree, and it does not affect at all. So it doesn't matter. So this material, this specific angle actually this material can be applied almost everywhere. It does not actually depend on the location of the cities. Okay, you want to use this one. So totally different concept. Okay, that does not. I'm sorry to confuse you actually, but we do not have to have the specific angle. Yeah.
All right. Thank you so much. I'm sure we've still got many questions, but we can be in touch, right?
Yeah. I'm very happy. Yeah. Thank you very much. Yeah, for everyone.
Yeah,
thank you.
Thank you so much for a brilliant talk and a very thought-provoking discussions afterwards. So
thanks.
So thanks a lot, and we'll pop up here. Sure. I think we're fine on the chat. Yeah. Thanks very much from the chat.
Thank you, everyone.
Thank you.
Yes.
Thanks so much.